R groups, anions. There are two anions that we have to be concerned about. And the easiest one, the side chain, is just our old friend acetate. Okay. And this is called aspartate, asp. Now we're in trouble, right? Because, well, we can't use the A because we use that for alanine, and we can't use the S because we use that for serine, and we can't use the P because we use that for proline. So we're going to use D. I don't know why they chose D. I didn't pick it. Okay. Now, instead of acetic acid, we could use propionic acid and make this our side chain. And this goes by the name glutamate, GLU. And again, if we're going to call aspartate D, and this is one methylene group bigger, let's use the single letter code E. So glutamate is simply the single letter code E. Now, if I do a titration curve with aspartate, for example, let's see what I find. Well, you know that if I do a titration curve, just like I did the last time, I'm going to find something that titrates at about 2, pKa of about 2. And what is that group? It's the carboxyl group, right? And I'm going to find something with a pKa of around 9.5. What's that? Yeah, the amino group. And now I find a third pKa. What's going on here? That's the pKa of the side chain. Okay? So the pKa for the side chain of aspartate is about 3.6. And the pKa for glutamate side chain is about 4.2. And that sort of makes sense, right? What's easier to protonate? If I start at high pH and start bringing the pH down, is it easier to protonate aspartate or glutamate? Raise your hand if you say aspartate. Raise your hand if you say glutamate. Yeah, remember, the higher the pKa, it means I don't have to push the pH down too low to protonate it. Why is it easier to protonate? It's got two methyl groups, right? Pushing electrons towards that carboxyl. A lot easier for something to protonate that. That carboxyl has an easier time, right? More electron density around it.